Open with the uncomfortable truth. Most database breaches do not begin with a magic database exploit. They begin with a credential, a service account, a forgotten host, an admin path no one reviewed for 3 years. Then the attacker moves. First the edge, then the app tier, then a jump box, then one database account with more privilege than it deserved. After that, PostgreSQL is no longer a database. It is the prize room. Recent breach history keeps teaching the same lesson. The Change Healthcare attack involved stolen credentials used against a remote access system without multi-factor authentication. The impact reached over 100 million people. Verizon's 2025 DBAs analyzed more than 22,000 incidents and over 12,000 confirmed breaches. Credentials remain the #1 attacker tool. CISA still updates its known exploited vulnerabilities catalog because active exploitation is not theoretical. Microsoft warns that attackers now use AI to accelerate lateral movement, social engineering, vulnerability discovery, and privilege escalation. So if your PostgreSQL cluster still trusts the network, trusts the admin host, trusts broad roles, and trusts permanent superuser access, you are not hardened. You are lucky. This video is not about fear for clicks. It is about building a production security posture that survives the first mistake. We are going to harden identity, network access, TLS, roles, role-level security, audit trails, OS controls, backup paths, and incident response. By the end, you will have a practical PostgreSQL hardening runbook you can apply to a real cluster. This is where most teams lie to themselves. They say, we have backups. Good. Backups help you recover data after corruption, deletion, or ransomware encryption. Backups do not erase data already stolen. Backups do not undo leaked customer records. Backups do not stop an attacker from reading replication slots, copying dumps, taking WAL archives, or creating a new privileged role before leaving. For PostgreSQL, the cost is not only the server. The cost includes every application depending on it. Billing stops. Orders stop. Support tickets explode. Compliance teams wake up. Legal asks what data was exposed. Customers ask whether their records were read. And GDPR, HIPAA, PCI DSS, and SOC2 all require breach notification. Find scale with breach size and negligence. The important concept is blast radius. A normal failure affects one layer. A security failure crosses layers. A compromised app user may become a database user. A database user may become a replication reader. A replication reader may expose the entire cluster. A superuser may change logging, disable controls, create extensions, load files, and remove evidence before exiting. That is why this video starts with the damage model before touching any configuration file. Hardening only makes sense when you know what you are actually trying to stop. Before you touch PostgreSQL.conf, build a threat model. Map every trusted path. Who connects? From where? Using which credential? Over what network? To which database? With what privilege? And what happens when that identity is compromised? A production PostgreSQL deployment has more paths than most people realize. Clients and application servers connect through a pooler or directly. Replicas receive streaming WAL. Backup agents pull base backups and WAL archives. Monitoring agents read statistics. DBAs connect for administration. Orchestration tools like Patroni talk to the control plane. Every one of those paths is an attack surface. The hardening rule is simple. Every path must identify, authorize, encrypt, log, and expire. Identify means verified identity, not just a username. Authorize means minimum necessary privilege, not broad roles. Encrypt means TLS at minimum, MTLS for critical paths. Log means centralized, tamper-resistant audit. Expire means credentials rotate and access is not permanent. If any path fails any of those 5, you have a gap. This video builds controls for each one. One setting does not harden a cluster. Hardening is a stack. Network controls limit who can reach the database. TLS encrypts the channel. Authentication controls verify identity. Privilege controls limit what each identity can do. Audit controls capture what happened. Recovery controls preserve the ability to recover after a breach. The order matters. Start with network exposure because it limits the attacker's initial reach. Then enforce TLS because credentials sent in plaintext are gifts. Then fix authentication, which means removing MD5 and trust entirely. Then rebuild roles, because most clusters have accumulated far too much privilege over time. Then enable structured audit logging. Then harden backup paths. Then test recovery. The baseline PostgreSQL.conf settings are not optional. Bind to specific IPs with listen_addresses. Set SSL to on. Set SSL_min_protocol_version to TLSV 1.2. Log every connection and disconnection. Log DDL as minimum. Set a log_line_prefix that captures user, database, application name, host, process ID, and transaction ID. Set log_min_duration_statement to catch slow queries that may indicate data extraction. These are your visibility foundation before anything else matters. PG_HBA.conf is not a configuration file you set once and forget. It is production security code. Review it like you would review application code that touches sensitive data. Because it controls which identities can reach your most sensitive data directly. The safe PG_HBA.conf pattern has 4 zones. App-tier connections use hostful with SCRAM-SHA-256 and a scoped subnet. Admin connections use hostful with cert and client-cert equals verify full from a specific jump host IP only. Replication uses hostful with cert and client-cert equals verify full from the replication subnet. Monitoring uses hostful with SCRAM from the monitoring host IP. And then an explicit reject rule for everything else. That last line matters. Implicit reject is fragile if rules are ever reordered. What you never put in PG_HBA.conf is trust for any network path, MD5 for any critical database, or a CIDR range that covers Office VPN, random Kubernetes pods, or the entire internal network. Each of those is a broad door. Broad doors are how attacker movement becomes attacker ownership. Network segmentation limits blast radius. TLS encrypts the channel between the client and PostgreSQL. That means credentials, queries, and result sets are not readable on the network even if it is intercepted. MTLS adds mutual verification. Both sites present certificates issued by a trusted CA. The server proves it is the real database. The client proves it is an authorized identity. For application traffic, TLS with SCRAM is the minimum. For administrative access and replication, require MTLS with client-cert equals verify full. This means the DBA certificate must be issued by your trusted CA and must pass full hostname or identity verification. A stolen password does not work without the matching private key. And a stolen key without the CA signature does not work either. Certificate hygiene is equally important. Set a 90-day rotation schedule before you ever need to rotate under pressure. Automate rotation using Cert Manager, HashiCorp Vault PKI, or your internal certificate authority. Set alerts 30 days before expiry. An ancient certificate that everyone has forgotten about is not just a risk. It is the kind of thing you discover during an incident at 2 in the morning when everyone is already angry. Do not find it then. Find it on a Tuesday when nothing else is on fire. The OS permission baseline for TLS key files matters too. The server.key file should be owned by the Postgres OS user, mode 600. If any other process can read the server private key, the entire TLS identity guarantee collapses. MD5 password hashing is not secure in 2026. It is fast to crack and provides no protection against offline attacks once a hash is exposed. Remove it. Replace everything with Scram SHA-256, which is the IETF standard Sultan Challenge Response Protocol. Set password_encryption to Scram SHA-256 in PostgreSQL.conf. Verify no roles still use MD5 prefixed hashes in PG_authid. Identity separation is the other half of authentication hardening. Human DBA accounts should be personal, auditable, and expire when the person changes roles or leaves. Machine accounts should be per service. The application role that connects from the billing service is not the same role as the application role that connects from the reporting service. Never share passwords between services. For administrative work, prefer short-lived credentials where your platform supports them. HashiCorp Vault can issue dynamic database credentials that expire after a set time. If you cannot use dynamic credentials, use valid until on roles created for specific maintenance windows. A role that expires at the end of the deployment window cannot be abused the following week. Superuser is not an operating model. It is an emergency tool. If your application connects as Postgres, or if your DBAs run daily work as Postgres, you have dissolved the privilege boundary that makes every other security control meaningful. A superuser can bypass row-level security. A superuser can load extensions. A superuser can copy files from the server file system. A superuser can alter logging. A superuser can remove evidence of their own actions. The privilege pyramid gives every function exactly the access it needs. App roles get select, insert, and update on specific tables in specific schemas. Report roles get select on reporting schema, with no write access. Maintenance roles can run vacuum, analyze, and reindex without touching DDL. Migration roles have DDL access in the application schema but carry a valid until timestamp, so they expire after the deploy window. The break glass superuser exists for genuine emergencies, is kept offline when not in use, requires a secondary approval, and every use triggers an audit record. Owner roles should be knowledgeon. If the application role owns the tables it writes to, then a compromised application role can drop those tables. Separate the object owner from the object accessor. Combined with default privileges per schema, this pattern means future objects inherit the right permission model automatically. Row-level security is your last line of defense when application logic fails. It does not replace application layer authorization. It backstops it. When a bug in your application sends the wrong tenant ID, or when an attacker gains database access directly, row-level security policies still filter the results set to only what the connecting role is allowed to see. The implementation has two required steps. First, enable row-level security on the table with alter table. Second, add force row-level security if the table is owned by the role that will also query it. Without force, table owners bypass all policies. Most teams forget the second step and discover the gap during a security review. Policies need realistic test coverage. Do not test only as superuser. Test as the actual application role using setRole. Run select count* and verify the row count matches what that tenant should see. And verify that your index structure aligns with policy predicates, because a sequential scan in a row-level security context can expose timing information even when the rows are filtered. Several SQL-level features deserve explicit review before you consider hardening complete. Extensions can load shared libraries into the PostgreSQL process and execute arbitrary OS commands in some cases. Audit which extensions are installed. Restrict extension installation to superuser. Remove any extension that is not actively used. The copy command with a file path argument reads or writes the server file system as the Postgres OS user. An application rule that can run copy-to with a file system path can read private keys, configuration files, and other sensitive data. Restrict copy file access to admin hosts only via pg_hba.conf. Security definer functions run with the privileges of the function owner rather than the caller. This is useful but dangerous without a locked search_path. Always set search_path explicitly in every security definer function. Also lock the default search_path at the cluster level in PostgreSQL.conf and parole with alter role set search_path. When something goes wrong, the first question is not philosophical. It is, who connected, from where, using which role, and what changed? If your logs cannot answer that within minutes, you do not have observability. You are flying blind during the most important investigation your team will ever run. PostgreSQL logging needs a log_line_ prefix that captures the timestamp, process ID, username, database name, application name, client address, and transaction ID. Log every connection and disconnection. Log DDL at minimum. For sensitive systems, use audit to add structured audit records for role changes, privilege grants, rights to sensitive tables, and administrative commands. The most important rule for audit logging is that logs must leave the database host before they are needed. Local-only logs are fragile. An attacker with host access can remove them. Configure a log shipper to forward to a central CM or object store immediately. Set alerts for specific events that should be rare, any new super user grant, any create extension, any admin login outside the maintenance window. PostgreSQL logs show database activity. They do not show every operating system action. If an attacker gets shell on a database host, you want to know about unexpected process execution, reads of private keys, changes under the data directory, suspicious outbound connections, and attempts to run tools like NC, curl, bash, Python, or package managers in places they do not belong. eBPF-based monitoring observes kernel-level events with low overhead. Falco-style policy rules watch behavior. Did the Postgres user spawn a shell? Did a process read server.key? Did a container open an outbound connection to an unknown IP address? Did someone exec into the pod during a non-maintenance window? These are not normal database behaviors. This layer does not replace PostgreSQL audit. It complements it. SQL audit tells you what happened inside the engine. OS runtime detection tells you what happened around it. A modern hardening plan needs both. Ransomware operators know that backups are the escape hatch from their leverage. So they look for backup servers, object storage credentials, WAL archive buckets, and snapshot policies before they encrypt anything. If the same credential that writes backups also deletes backups, you handed the attacker the broom. Separate backup identity from database identity. The backup role should have minimum PostgreSQL privileges, replication for PG_base backup, PG_read_all_ settings, and PG_read_all_ stats. Nothing more. Object storage should use restricted IAM credentials. The right credential for WAL archiving should not have delete permission on the bucket. Enable object lock or S3 style immutability where available. Test restores on a schedule. Monthly is the minimum for production clusters. Backup success means a file exists somewhere. Recovery success means the database starts from that file, reaches the correct target time, and passes application level validation. Those are very different things. High availability deployments increase the number of access paths. More nodes means more credentials, more automation, more failover scripts, and more humans who say they will clean that up later. Later is where incidents breed. Every replica is a door. Every Patroni or Repmer credential is an identity that can be compromised. Replication roles should be limited to replication. Use the replication attribute and nothing else. Require hostful with client cert equals verify full for every node-to-node replication connection. Monitor replication slots. A stale logical replication slot accumulates WAL and can expose sensitive data to the subscriber. Do not make replicas weaker than the primary. Apply the same PG_HBA.conf hardening, the same TLS configuration, and the same OS security baseline to every replica node. During failover, a replica becomes primary at exactly the moment when everyone is stressed and making fast decisions. If the replica has weaker security than the primary had, you just promoted a weaker security posture into the critical path. PostgreSQL hardening fails fast when secrets are sloppy. Check the usual crime scenes. .env files committed to version control. Docker images with passwords baked into environment variables. CI pipeline logs echoing password or connection strings. Shell history files containing PSQL commands with inline passwords. Use a secret manager. Inject secrets at runtime. Keep database passwords out of application code, out of Docker images, out of CI logs, and out of shell history. Rotate database passwords quarterly at minimum. Rotate TLS certificates on a 90-day schedule. Short-lived credentials are architecturally better than permanent credentials. A credential that expires in 1 hour after the job completes cannot be abused for months by someone who found it in a log file. A secret that never changes is not a secret. It is a fossil with database access. A hardening plan should include the bad day. When suspicious activity appears, the worst thing you can do is improvise. Improvisation during a live incident produces deleted evidence, missed attacker persistence mechanisms, and premature reconnection of applications to a still compromised database. Write the runbook before you need it. The 6-step response flow is detect, isolate, preserve, rotate, restore, verify. Detect means the alert fires where someone observes the anomaly. Isolate means blocking suspicious network paths and removing the affected node from service where safe without losing evidence. Preserve means snapshotting disks, exporting logs to a write-once location, and recording a complete timeline before changing anything. Rotate means changing every credential that touched the compromised path. Inside PostgreSQL, the triage queries matter. Check PG_stat_activity for active sessions that do not belong. Check PG_roles for unexpected superusers and any role with role_passels set. Check PG_settings for non-default settings that changed at runtime. Check PG_extension for unexpected extensions. Check PG_replication_slots for stale or suspicious slots. After containment, do not reconnect applications until you have verified the role model, TLS configuration, PG_HBA.conf, audit logging pipeline, and backup chain integrity. Here is the plan. Week 1, map every door. Inventory every role in PG_roles. List every superuser and replication role. Audit PG_HBA.conf and remove every trust rule, every MD5 method, and every CIDR range that is broader than necessary. Lock listen_addresses to specific IPs. Enable log_connections, log_disconnections, and log_statement equals DDL. Map every backup path and the credentials used. Week 2, encrypt everything. Deploy TLS on every connection path and enforce SSL equals on. Upgrade administrative and replication paths to MTLS with Verify Full. Migrate all authentication to Scram SHA-256. Rotate old TLS certificates and database passwords. Move secrets out of code and into a secret manager. Week 3, rebuild privilege from scratch. Create task-specific roles for app access, reporting, maintenance, and migrations. Convert table owners to knowledge and roles. Revoke create on the public schema from public. Set default privileges per schema. Enable RLS on tenant isolated and sensitive tables. Audit every installed extension, every FDW, and every security definer function. Week 4, close the detection gap and drill the response. Install Audit and ship logs to a central CM. Set alerts for new superuser grants and new replication roles. Deploy eBPF or runtime detection on your database hosts. Lock object storage with immutability and delete restrictions. Run a breach drill using the incident runbook you just wrote. Find the gaps in a controlled environment rather than in a real incident. That is the difference between a hardened cluster and a cluster that is just waiting for its turn. Security is not a checklist you finish. It is a posture you maintain. The cluster that survives a real incident is the one that assumed breach before the breach happened. Lock the network. Verify identity on every path. Minimize privilege to the absolute minimum each role needs. Log everything and ship those logs off the host before you need them. Test recovery before the incident forces you to discover whether your backups actually work. Start week 1 on Monday. Inventory every role. Audit PG_HBA.conf. Remove trust. Remove MD5. Lock listen_addresses. Enable connection logging. That is one afternoon of work. By the end of it, you will know every door into your cluster. That knowledge alone changes your security posture. If this video helped, leave a comment telling me which week of the hardening plan you are starting with. Subscribe for the next deep dive. The next video goes deeper into PG_HBA.conf with a full production walkthrough. See you there. Dr. Ibrar Ahmed. PostgreSQL Deep Dives. Advanced Database Engineering.